Well, after building up a lot of machinery to understand eigenvectors and eigenvalues of a matrix, it's time to see some of the payoff. We'll return to the population model of foxes and rabbits that we introduced several lectures ago and see what we can now say about them. Remember, this was just a model, which means it's not going to perfectly represent what may happen in reality. We'll make some simplifying assumptions, obtain some results, and hope that these results will give us some insights, even if the model isn't perfect. We let f sub n represent the population of foxes at time n, and r sub n represent the population of rabbits at time n. We make the assumption that the number of foxes and rabbits doesn't have to be an integer. This is unlikely to affect the character of the results we obtain, especially when the number of foxes and rabbits is large, and the fractional difference between integer and non-integer values is small. Furthermore, we'll assume the population vector, f sub n plus 1, r sub n plus 1, at time n plus 1, depends linearly on the population vector, f sub n, r sub n, at time n, according to the following model. Let f sub n plus 1 equal 0.6 times f sub n plus 0.5 times r sub n, and let r sub n plus 1 equal minus p times f sub n plus 1.2 times r sub n. Recall that the coefficient 0.6 for f sub n represents the fact that foxes die without rabbits. In particular, 40% die off at each time step if there are no rabbits. The minus p coefficient for f sub n shows that the number of rabbits is negatively influenced by the presence of other foxes. In other words, foxes eat rabbits. We call p the predation parameter. We'll explore what happens for various values of p. And the 1.2 coefficient indicates that without foxes, the number of rabbits multiplies by 1.2, which means it grows by 20% at each time step. This linear system can be expressed in matrix form as we see here. If we let x sub n be the population vector at time n, then we see the time n plus 1 population vector is a matrix A, shown here, times the time n population vector. So repeated multiplication by A gives the successive population counts as time grows. This means that if we are given the initial population vector x naught, which is f naught r naught, then the time k population vector x sub k is given by a to the k times x naught. The question we want to answer is, what happens as the number of steps k goes to infinity? What is the long-term behavior of this system? Do rabbits and foxes thrive, or do they die off? And what happens if we vary the parameter p? We'll study the cases where p equals 0.175, 0.16, and 0.10. We'll see exactly how the answers depend on the eigenvalues and eigenvectors in each instance. Let's carry out the first calculation for p equals 0.175. We calculate the eigenvalues of A by taking A and subtracting lambda off the diagonal to get A minus lambda I, which is the matrix 0.6 minus lambda, 0.5 minus 0.175, 1.2 minus lambda. Now, taking the determinant of this matrix, you'll get the characteristic polynomial, which is lambda squared minus 1.8 lambda plus 0.8075. This polynomial has two roots, which can be found using the quadratic formula, and these are lambda equal 0.95 and 0.85. And remember, they are the eigenvalues of A. Then we find eigenvectors associated with each eigenvalue in turn. For lambda equals 0.95, we plug in lambda equals 0.95 into the matrix A minus lambda I, and you'll get this matrix. We expect this matrix to not be invertible since the eigenvalues occur precisely where the determinant of the matrix A minus lambda I is 0. So it should have non-trivial null space. And indeed it does. You could compute the null space by solving the homogeneous system, where you multiply this matrix by a vector x and set it equal to 0 and solve for x. But for a 2x2, you can often see a solution by inspection. In this case, I notice one column is a multiple of the other, a sure sign the matrix is not invertible. In fact, the ratio of the first column to the second column is minus 7 to 10. So if I multiply this matrix by the vector 10, 7, you will see you get the 0 vector. So one eigenvector for the eigenvalue 0.95 is the vector 10, 7. In a similar way, you can find an eigenvector for the eigenvalue 0.85 by subtracting 0.85 off the diagonal of A and finding a vector in the null space of that. Try this, and you'll find an eigenvector is 2, 1, or some multiple. So now we've found the eigenvectors and eigenvalues when the predation parameter p equals 0.175. What about predation parameters p equals 0.16 and 0.10? I will not bore you with computing them. You could do them by hand, as we've done. But now that you understand the meaning of the eigenvectors and eigenvalues and how to compute them, you could let software do it for you. Here's a summary of what you'll find. So here you see the eigenvalues and eigenvectors vary as you change the predation parameter. When p equals 0.175, the eigenvalues are both less than 1, and the eigenvectors are as shown. When you lower the predation parameter to 0.16, so foxes eat fewer rabbits, the eigenvalues are 1 and less than 1, and the eigenvectors have changed a little bit too. Finally, when you lower the predation parameter from 0.16 to 0.10, one of the eigenvalues now exceeds 1, and the eigenvectors have changed a little also. So, what do these computations tell us? Well, for starters, they begin to give us clues as to what is happening. Remember that when eigenvalues are bigger than 1, that indicates an eigenvector direction that is expanding. And when the eigenvalue is less than 1, that indicates an eigenvector direction that is contracting. So we get a clue just from thinking about the eigenvalues. If the predation parameter is high, then both eigenvalues are less than 1, so this indicates the population vector is contracting along the special eigenvectors. We'll see this also means the population vector is contracting everywhere else. So let's do a computation. First, recall that if the initial population vector, F0, R0, can be written as a linear combination of the eigenvectors, call them V1 and V2, then we have derived a nice formula for the time k population vector. Let's say the initial population x0 equals F0, R0 can be written as some linear combination of eigenvectors C1, V1 plus C2, V2. Remember, this will be possible if the matrix is diagonalizable, so there is a basis of eigenvectors. The coefficients C1 and C2 of our linear combination can be solved from the initial populations F0 and R0 if we wish, since this is just a system of equations and unknowns C1 and C2. Then A times this x0 just multiplies the V1 and V2 by their corresponding eigenvalues, like this. And if we keep multiplying on the left by A, we see that the eigenvectors just produce a factor of a corresponding eigenvalue each time. So then x sub k, the time k population vector, is a to the k times x0, and that is just c1 times lambda 1 to the kth power times v1, plus c2 times lambda 2 to the kth power times v2. This is a very simple formula. And in general, computing a to the k would be very much harder, especially if the matrix were large. It may be worth pointing out that if A is diagonalizable, then this formula is exactly what you'd get by multiplying x naught on the left by p d p inverse, where p has eigenvectors of A as columns, and D is a diagonal matrix with diagonal entries lambda 1 and lambda 2. Because P inverse times x0 is exactly the calculation you would do to use the initial conditions to find C1 and C2. With this formula in mind, let's now consider 3 scenarios. In the case of high predation, if we look at what this means for P equals 0.175, then we see that f sub k r sub k equals C1 times 0.95 to the k times the eigenvector 10, 7, plus C2 times 0.85 to the k times the eigenvector 2, 1. Notice how the 0.95 to the k and 0.85 to the k go to 0 since both these terms come from eigenvalues that are less than 1. This means both terms in this expression eventually go to the 0 vector. In other words, you can interpret this as saying that as k goes to infinity, no matter what C1 and C2 are, and remember they come from the initial conditions, the two populations will approach the 0 vector. In other words, both populations go extinct, no matter what populations you start with. Graphically, we can plot the eigenspaces for 0.95 and 0.85 on the Fox-Rabbit plane. Here we see the 0.85 eigenspace, marked by E sub 0.85 in the diagram, lies along the vector direction 2, 1. Any point along this eigenspace represents a population vector where the number of foxes is twice the number of rabbits. So for a vector on this eigenspace, the population vectors will, after one time step, remain in that ratio 2 to 1, but both will be multiplied by a factor of 0.85. Thus, both populations decrease by 15% in each time step. Similarly, the 0.95 eigenspace, denoted by E sub 0.95 in the diagram, lies along the vector direction 10, 7. So the fox to rabbit ratio is 10 to 7 along this eigenspace. After a single time step, the population ratio will remain the same because it is an eigenvector, but both populations will be multiplied by a factor of 0.95. So both populations decrease by 5% each time step. And if you start with the population vector at any other point, you can write the vector of populations as a linear combination of eigenvectors that live in the eigenspaces. The contraction will be faster along the eigenspace direction for 0.85. So this point on the 0.85 eigenspace moves towards the origin faster than this point on the 0.95 eigenspace. So the net effect is that a point that is not on either eigenspace will, as time progresses, skew towards the 0.95 eigenspace because the component in the 0.85 eigenspace will disappear quicker. And these curves indicate the shape of the path that a point follows. See how they skew towards the 0.95 eigenspace? No matter where you start on this diagram, the population vectors eventually go to 0. And we can see how fast they go to 0. The eigenvalue closest to 1, which is 0.95, is the limiting factor in how slowly the populations die off, because 0.95 to the k goes to 0 slower than 0.85 to the k. Now this was for the predation parameter set at 0.175. In this case, we got extinction for both foxes and rabbits. It shouldn't surprise us that if we lower the predation parameter, we may see the populations survive. So let's look at the case now when we lower the predation parameter to 0.1. In that case, the eigenvalues are 1.1 and 0.7. And we calculated the eigenvectors already as 1, 1 and 5, 1. Then, using the same formula before, but with different eigenvalues and eigenvectors, we see that the time k population vector is C1 times 1.1 to the k times the eigenvector 1, 1, plus C2 times 0.7 to the k times the eigenvector 5, 1. Notice that for large K, the first term dominates. It actually blows up. The second term goes to 0 as K grows. This is now saying something more interesting than when the predation parameter was large. Remember that C1 and C2 are determined by initial conditions. So if C2 is 0, then the initial population lies along the eigenspace for 1.1, in which the fox to rabbit ratio is 1 to 1 because the eigenvector is 1, 1. So if you start with fox to rabbit ratio 1 to 1, then at each time step, the population ratio stays the same, but both populations increase by 10%, as indicated by the factor 1.1. So the fox and rabbit populations over time will grow and flourish. But if you start with initial condition where C1 is 0, then the initial population lies along the 0.7 eigenspace, which means the initial ratio of foxes to rabbits is 5 to 1, since the eigenvector is 5, 1. In that case, the populations each time will decrease by 30% because the eigenvalue is 0.7, but the ratio will remain 5 to 1. And in this diagram, the 1.1 eigenspace is denoted by E sub 1.1, and the 0.7 eigenspace is denoted by E sub 0.7. For the points in the 1.1 eigenspace, you get an expansion by 10% at each step. And for points in the 0.7 eigenspace, you get contraction by 30% at each time step. Now things get interesting when your initial populations do not lie in the eigenspaces. As before, you'll need to take the initial vector of populations and write it as a linear combination of eigenvectors 1, 1, and 5, 1. Doing so produces vectors along the eigenspaces that sum to the initial vector, and the coefficients C1 and C2 just tell us how large these component vectors are in relation to the eigenvectors 1, 1, and 5, 1, shown by the arrows along the eigenspaces. If C1 is greater than 0, then the first term is non-zero and yields a vector of populations positive in each coordinate. The first will quickly become larger than the second term, if it isn't already, and when that happens, the populations will be growing by a factor of approximately 1.1 at each time step. In addition, the ratio of foxes to rabbits will be close to 1 to 1. We can see this in the diagram because when C1 equals 0, you lie on the 0.7 eigenspace with eigenvector 5, 1. So if C1 is bigger than 0, then that's all the points to one side of the 0.7 eigenspace. Which side? Well, it's the side in the direction of 1, 1, so it must be the top side of the 0.7 eigenspace. This is just the set of points where the ratio of foxes to rabbits is strictly less than 5 to 1, which kind of makes sense. If there are fewer than a certain ratio of foxes to rabbits, then both populations should survive and flourish. To summarize, if C1 is bigger than 0, which corresponds to a fewer than 5 to 1 ratio of foxes to rabbits, then the populations flourish in a 1 to 1 ratio of foxes to rabbits, and they grow by about 10% in each time step. In the diagram, you can see that this happens in the region between the 1.1 and 0.7 eigenspaces in the first quadrant. It also happens in the region to the left of the 1.1 eigenspace in the first quadrant. The curved paths show the direction that the population vectors point in this region. No matter where you start, the points move towards the 1.1 eigenspace and eventually track along it. Now, if C1 is less than 0, you can see that the first term will be a vector that is negative in both components, for both foxes and rabbits. This corresponds to the shaded region in the diagram. The first term may be outweighed by the second term if the second term is quite positive at the start, but eventually the first term will grow in absolute value and dominate, leading to one of the populations going negative. Of course, the model breaks down here because you can't have negative populations, but it suggests extinction for one of the populations. We can see which one goes extinct first by looking at the diagram. If C1 is less than 0, this happens when you are below the 0.7 eigenspace in the diagram, which is where the ratio of foxes to rabbits is greater than 5:1. If you start at a point in the first quadrant but below the 0.7 eigenspace, you will see that the points there will move downward to the left because they want to approach the 1.1 eigenspace, and they are on the negative side of the eigenspace. This leads to extinction for rabbits first, which makes sense since in this region there aren't enough rabbits to feed all the foxes. So even though the model breaks down here with negative rabbits, we learn something. The critical ratio to pay attention to is 5 foxes per rabbit. Any more than that and you have extinction of rabbits, and therefore foxes unless they eat something else. But any less than that and both populations flourish. Let's do an example. If the initial population vector is 4, 1, then we can solve for C1 and C2 to find which linear combination produces 4, 1. This is just solving a linear system. You can use an augmented matrix if you wish, and when you do that, you'll get C1 equals 1/4 and C2 equals 3/4. This is equivalent to multiplying by P inverse if P is the matrix of eigenvectors. So C1 is bigger than 0, means that both populations flourish. On the other hand, if the initial population vector is 18, 2, then when you solve for C1 and C2, you get C1 equals -2 and C2 equals 4. And since C1 is negative, we know the rabbits are headed for extinction. It's pretty amazing what we learned from the mathematics. The 5, 1 eigenvector gives us the critical ratio between foxes and rabbits that determine whether rabbits eventually go extinct or not. Finally, let's look at what happens when the predation parameter p equals 0.16. The eigenvalues are 1 and 0.8 with eigenvectors 5, 4 and 5, 2. And based on other examples, you can probably guess what will happen here. I encourage you to take a moment now to sketch a diagram of the fox-rabbit plane and figure out what is happening to points in the plane at each time step. Take a moment now to think about it. Okay, so if you were to draw the diagram, it would look much like the previous diagrams, with eigenspaces E1 and E.8 slightly shifted from the prior examples, lying along the 5, 4 and 5, 2 vector directions. The key insight is that the eigenvalue 1 is not expanding or contracting. So if you take any initial population vector and write it in terms of the components in the eigenspace directions, then any component in the 5, 4 direction just stays put, with no change at each time step. Any component in the 5, 2 direction will contract by a factor of 0.8 at each time step. So that component eventually vanishes and everything moves towards the eigenspace corresponding to the eigenvalue 1. Which means that if the component of the initial population vector in the 5, 4 direction is positive, eventually the population vector will converge to a point on the E1 eigenspace. Look at all these paths. So the long-term behavior is that the populations neither grow nor go extinct, but approach a stable population in a 5:4 fox to rabbit ratio. On the other hand, if the component of the initial population vector in the 5, 4 direction is negative, the population vector will converge to a point on the E1 eigenspace below the x-axis. The model breaks down there because populations can't be negative, but what we observe, if we follow this path below the 0.8 eigenspace, is that rabbits will go extinct first. And this happens in this shaded region. Who knows what happens to foxes after that? So you see the crucial ratio here is the ratio of foxes to rabbits along the 0.8 eigenspace, which is 5 to 2. If you have more than 5 foxes to 2 rabbits, then the rabbits go extinct. If you have less than 5 foxes to 2 rabbits, the populations converge to a 5 to 4 ratio and remain stable. So what have we learned from a model, even if it isn't perfect? Well, the idealization with simplified assumptions was still valuable because we saw the general behavior of a system as you vary the predation parameter. We saw that it confirmed our intuition that when the predation parameter is high, or the ratio of foxes to rabbits is high, then the populations go extinct. But we learned more. We began to see the critical values at which the behaviors changed. We began to understand the qualitative behavior of such a system much better. This brings up some other points that may be helpful to stress here. Recall from the very first lecture I mentioned 4 themes that I said that I would emphasize throughout this course. All 4 of these themes make an appearance in our modeling exercise. The first theme is that linear ideas arise everywhere. And indeed, our model shows us that we can use linear algebra to understand a very basic model of population dynamics between foxes and rabbits. Now, I know you may object and say, but you chose a linear model to start with. Of course we needed linear algebra to solve it. But that brings me to my second point. Even if this linear model doesn't reflect reality, we can often use linear models to approximate reality. If there were some nonlinear behavior in a more accurate model of fox-rabbit dynamics, one way we would begin to get a sense of what's going on qualitatively is to first start with a linear model. In fact, the word you often hear in this context is linearization. Sometimes you'll hear people say they linearized a model because it was more tractable or it gave some good qualitative information. And this emphasizes the second theme I mentioned at the start of this course. That to understand nonlinear things, we often approximate them by linear things. The third theme is that linear algebra reveals hidden structure that is both beautiful and useful. Eigenvectors and eigenvalues were hidden to us at first. If we didn't know about them, we wouldn't have been able to say something as refined as which critical values of the populations in our linear model would lead to extinction. We wouldn't have been able to say what the long-term ratio of populations would be. Both of these things are related to the eigenvectors of the linear transformation that's at the heart of this model. Nor could we say how fast that convergence would take place, which was related to the size of the largest eigenvalue in absolute value. We saw the usefulness of eigenvectors and eigenvalues. And I hope you also saw in some of the reasoning the beauty of knowing such objects. When you encounter an arbitrary linear transformation, you aren't handed the right way of thinking about what it does because the usual coordinate system may not be the best way of thinking about its action. But the eigenvectors and eigenvalues are the right way to think about a linear transformation. The eigenvectors produce the best basis to view the action of the transformation. And finally, the fourth theme we stressed was the power of linear algebra deriving from the interplay between geometry and algebra. What you see from our analysis of foxes and rabbits is that we continually moved back and forth between the algebra and the geometry. The algebra in the terms of the expression and how to manipulate them, and the geometry in the diagrams, which often gave us intuition for thinking about what we encountered. Each one gave us insights into the other. And this is such a powerful idea in mathematics. If you know multiple ways of understanding a concept, you can move back and forth between them to choose whatever view is most convenient for you to solve the problems you want to solve.